Hello, hello, hello.
Hey Professor, before
Hey,
we start,
yeah,
I have a question about the face-to-face test.
yes.
So I did it, and one of the questions I got wrong was I think it wanted velocity, but in the question it said speed.
Hmm.
And I mean, and the two answer choices I had were negative half a meter per second and positive. And I took the positive one because because the question said speed.
Hmm.
And normally in the later chapters, you can tell when they say speed, they just mean velocity. But in like the first and second chapter, they sort of tell you to know the difference between speed and velocity.
Right.
And so, I mean, I just wanted to know if if there was any chance I could get the points for that question back.
Actually, the problem is a little bigger than what you're realizing here. It's not, I was actually asking for the speed, but there's a whole different process that has to go, that you have to go through to calculate the average speed as compared to the average velocity. Uh, we still have a couple students left that are taking this, so I can do it at the end of class or sometime not on video, but I'll explain it to you. But the big thing is uh, final our average velocity is the x of t, the displacement vector at the final
Yeah.
time t minus the displacement vector at the initial time t0 divided by the time taken. Whereas the average speed is the distance traveled divided by the time taken. And if you have a function, for instance, a x of t that's not just like linear, then sometimes you have to look at the graph or make some sense of what the actual x of t is so that you can actually figure out what the average speed is as compared to the average velocity. I can flesh that out a little bit more for you, like I said, when I'm not on video. But that's what ultimately went wrong, and I know a lot of students got it wrong. I thought I was doing a really big favor by putting so many of the previous problems on there. The good news is that I'm aware that the test average is as high as I would have liked it to be, and I'm sort of taking some of the blame on that. So I'm going to offer some stuff for you guys to do to improve your face-to-face test scores one and two. So right now, what I'd recommend you do is make sure you can get back into test one and test two and get screenshots of every problem in there, not just the ones you got wrong, but every one of them, and start doing those, figuring out how to do them, not necessarily looking them up, but figuring out how to do them. If you need to look them up to do that, then look them up, close it, and then start to solve it again. If you get stuck, look at it again, close it, then start solving it again, that kind of thing.
Okay. All right.
So,
Thank you.
yeah, no problem. Yeah, that I know exactly which problem you're talking about because I had several people ask me about it. So you're on the right page. That's the that's the good news. Everybody's in the same boat with you. Anything else, Giovanni?
No, it was just that one.
Okay. Yeah, don't worry. We'll get you hooked up pretty soon anyways. All right. It's about time, but we're still don't have everybody here, so I'm not really sure what's going on with this. All right, guess I'll get ready to roll.
So I had a question.
Yes, go for it, Dylan.
So
Or yeah, it's Dylan.
yeah, I was doing the chapter 9 concept stuff,
Mm-hmm.
and I've been having trouble like relating the work to force, to kinetic energy to impulse. Like they're talking about how it's like something with different masses travels over a distance versus a time. They'll have the same work, but uh, I think if it was over a different distance, like the kinetic energy would be different. But if it was over a time, like it the way it was doing it is just I thought the mass tied more into it, but they were talking about they basically took the mass out of the equation and was just using the force and the work. So going between the three or four different things, I've just been having trouble and getting really confused.
Gotcha. Was this chapter 9 conceptual homework that you were working with, or something totally
Yeah,
unrelated?
yeah, the
Okay, yeah,
chapter
I
nine
saw some
conceptual.
of those were kind of not trivial to do. So I'm certain that's part of the problem. What I will tell you is, and we can, ask very specific questions towards the end if you want. Uh, but what I will tell you is that uh, impulse, for starters, is a change in momentum. So you can literally calculate P final minus P initial, which is a very easy thing to calculate usually,
Uh-huh.
and that's the impulse. But then there's another version of calculating the impulse, which is the integral of f dt. That's a whole different calculation, but it's the same quantity, and therefore sometimes you're just smarter to calculate the delta p part instead of the f delta t. And then not only that, you can also calculate the average impulse, if you will, by taking the average force and multiplying it by the duration time of the force. So there's like three different ways you can do that. And then if you combine work with it, work is basically equivalent to, in some sense, is equivalent to energy. So you can take a work and say that completely is converted into change in potential energy, or you can say it's completely changed into change in kinetic energy or stuff like that. So what we'll do is at the end of class, if you want to pull up some specific concept questions, we'll address them in real time. I think I can finish up the part that I plan on doing this tonight. I think I can finish doing that pretty quickly, and maybe even have a couple minutes towards the end of class to reserve for that question if you want. Also, regarding the questions you had about the orbital stuff that we were working on last time, I
Uh,
have found a bunch of different ways in which we can solve those problems. So I can address that too now. Or probably just my intent is to make a couple of videos on it, probably this week, and that'll explain everything. But I just want to let you know I hadn't just completely fallen off the face of the earth with those questions you asked me about the orbital stuff.
okay,
All
cool.
right. Anybody else have any questions? It looks like we've got just about everybody here. Yeah, go ahead and chat me your first and last name. It looks like most of you have already done that, or a few of you already done that. Uh, I was diagnosed Thursday with a medical issue that might be the reason that I yawn a lot. I'm not sure. So at least now I can point my finger at that thing that makes me fall asleep. I have what's called an adenoma, which is not cancer. So that's a good thing, but it's in my pituitary, or excuse me, in my parathyroid, not pituitary, but in my parathyroid, I have basically a tumor, and that's causing me to have hyperparathyroidism, and that's making me really, really sleepy, which makes me feel good because for all this time I thought I became lazy like around 2020, 2019, and it appears I've been lazy, but it's been for a reason. I'm like freaking exhausted and falling asleep at the drop of a hat. So, anyways, I apologize again for the repeated yawns, but at least now I have a reason. And there goes another. Okay. So when we last met, we had worked through some two-dimensional problems in conservation of momentum. Remember, conservation of momentum is a quantity or is a idea that has a very specific condition. Can anybody tell me off the top of your head what condition must be true for linear momentum to be conserved? I do sort of expect like virtually everyone not to know. Uh, not because I didn't tell you, but because that's the nature of the beast. It turns out that students always hear conservation of momentum, but for some reason they never hear the preconditions. And that was part of that derivation I showed you. So I started off showing you Newton's second law. Newton's second law of motion as in the way that he introduced it, which was the summation of the external forces or the net external force acting on the system is equal to dp dt. That's the instantaneous rate of change of linear momentum p with respect to time. So the dp dt is equal to the summation of the forces. In the event that the summation of all the forces is equal to zero, then you have dp dt equal to zero. And the only way a derivative can be equal to zero is if the function is a constant. Excuse me, is if the function is a constant. So that specifically is conservation of momentum. When you say the momentum is a constant, then that's conservation of momentum. Okay, so the necessary requirement for momentum to be conserved is that the net external force on the system is zero. That means you can have all sorts of internal forces, like if your system is two cars approaching an intersection, all the forces that car A puts on car B are all okay. They're internal forces. They're one part of the system acting on the other part. So that's good. Not only that, the forces that are actually external would be like the force of gravity, which is the weight, but the weight is counteracted by the normal force. So those two add up to give you zero. And then it turns out pretty much all you have is wind, air resistance, and maybe some friction forces. And if those friction forces are quite small compared to the other forces that the two things are putting on each other, then sometimes you can approximate the situation such that the net external force is approximately zero. So that's what we use it. But I just want to remind you guys that momentum is not in general conserved. It's conserved when the net external force is zero. Is zero. Okay. So now that we have that out of the way, and I've shown you a couple of ways to solve various problems, I'm going to go ahead and work on some additional problems. So I'm starting off with example 910. This is essentially the same as your example in your book 910. So what we have is a little bullet of mass little m with a velocity nu. That's the Greek letter nu. It looks like a V, but it's a nu, and it's moving towards a big block whose mass is big M. And then what's going to happen is the net external force acting on this system, which includes the bullet and the big hanging block, the net external force on that is zero. So the bullet is going to pierce and penetrate the actual big block M. And at that point, momentum will be conserved. So we can use conservation of momentum to determine what velocity the block will leave hanging straight down will be its initial position, and what velocity it leaves from that hanging straight down position can be determined that way. And then you can use conservation of momentum. Excuse me. Then you can use conservation of energy to figure out how that height that it goes is related to the initial velocity. So let me show you what's going on here. Solution. The summation forces is equal to dp dt implies the summation forces equals zero, implies dp dt equals zero, and that implies p equals a constant. So from that, I get lowercase m, lowercase v. That's the only thing moving initially, and it's moving in the horizontal or x direction. Yeah, Jen? Oh, you want to see the screen?
Yeah.
Y'all really want to see the screen?
Yeah.
Thank you for calling my attention to that. Yes, I completely forgot because I am a goober. So let's do this. Okay. Now that should work. Okay, hopefully. There you go. So it should come up soon, and you're going to be very excited with how much stuff is already written there because I've been filling it out, thinking y'all are watching. So there's our solution. Notice I have a drawing. I said, consider the ballistic pendulum shown below. Now, in principle, I think you've already done this lab in your lab. That's where I covered it, but I decided to cover it in here just in case your instructor, your lab instructor, didn't go over it enough, or in case you needed to see it again. So that's why I'm doing it again. What I've concluded is the summation of the forces acting on the system is zero. Therefore, the momentum is a constant. That's conservation of momentum. And the initial momentum is just the momentum of the bullet. So it's just literally m times v, or m times nu. Now, after the collision, it's going to be m plus m, because we're assuming that this block is actually going to be big enough and heavy enough to completely stop the bullet, and the shell, the projectile, is going to embed itself inside of it, so that the mass is now not just m, but m plus m. And it's going to leave with a velocity that I call v prime, like that. Okay. Now that's conservation of momentum, and from that we can say that v prime is obviously equal to m over m plus m, like that, times the initial velocity. Now that I have that, I can now figure out what velocity the m plus m has before it goes into raising that self. So remember, this big block is hanging from the ceiling and it's going to swing. And in some sense, you could imagine some kind of device stopping it at some max height, or at least recording its max height. So that's what we're trying to do, is we're trying to work out a relationship between the height h and the initial muzzle velocity of the bullet. So in other words, the velocity that the bullet had when it entered or just before it entered the block. So now I'm going to use conservation of energy. And I can, in principle, use the conservation of energy that I showed you guys, but I really don't need all that because this is a much simpler case. So I can use U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. That all works, but we're not going to have any of this stuff. So because of that, E loss is going to zero, workout is going to zero, work in is going to zero. And in fact, the potential energy initial is zero because I'm starting to study it when it's hanging down. So the red figure that you see where it has the mass m plus m and it's red and it's still hanging down, it only has kinetic energy at that point. And then it swings up, and at that point, it only has potential energy and no kinetic energy. So the final kinetic energy is going to be zero. From this, we can see that we have 1/2 m plus m v prime squared. That's the velocity it has right after the collision. That's equal to m plus m times g times h. So I can, in principle, for starters, cancel out this m plus m, and I can also plug in this new value of v prime. So now I have 1/2 of what I had was m over m plus m times v. And then this whole quantity has got to be squared. So basically, I got rid of the m plus m by canceling out on both sides, and this is just 1/2 v prime squared. That's equal to g. That's equal to g times h. So I can finally write this as m over m plus m squared v squared is equal to 2gh. And finally, I can work out that the muzzle velocity is equal to, in this case, I'm going to say m plus big M over little m, because I'm ultimately going to multiply by m plus m over m squared. And I'm going to do that to both sides. That'll give me the m plus m squared. And then I'm going to take the square root of everything. But since it's squared, that can come out in front, and I just get left with 2gh in the square root. And that's the ultimate result. Anybody have any questions on that one? So that there was a lot of algebra that took place in there. It wasn't too terribly much. Hopefully y'all can see it, but if you didn't, definitely you want to try to work it out. And if you can't, you want to contact me so I can help you, or contact another student that might have seen it. But everybody get that? That's how the muzzle velocity, the new symbol there, is related to h, the height. So as long as you know the mass of the shell, the mass of the block that it's going to be embedded in, and then the height, the maximum height that it'll reach, then you can automatically figure out the muzzle velocity of the projectile. Any questions on that? Okay. So that was just another problem continuing on after the 2D, or excuse me, after the one-dimensional head-on collisions with elastic collisions and all that good stuff. So we've already covered all that with 9.8, examples 9.8, 9.9, and all that good stuff. Now we're going to go on to example 9.11. It says a train can have a train car has a mass of 10,000 kilograms and is traveling at 8.0. I'm going to call that 8.00 meters per second. And I'm going to assume that only the last two zeros in that 10,000 kilogram are not significant. So it says a train car has a mass of 10,000 kilograms and is traveling at 8 meters per second when it collides and sticks to an identical train car at rest. Calculate how much of the initial kinetic energy is lost. I can actually, I pulled the numbers from the previous example, because in example 9.11 in your book, there actually are referring to a previous example, and they gave you all those numbers, but they didn't give you the example, the numbers in the example. I ended up working this with just symbols, so I can do the same thing again. Let me show you what we're going to do then. Whoa, I don't know what I'm doing. I went to write solutions and I ended up writing subject. So here's the solution. So what we're going to do is we have a train car that looks like this, and it has a mass m, and it's moving with some velocity v, and it's going to run into an identical train car of mass m, but its initial velocity is 0. So stationary. After the collision, what's going to happen is we're going to have the two train cars tied together, and therefore their mass is now 2m, and they're moving with a new velocity v final. Okay, but they are stuck together. So what we'll do is use conservation of momentum. Applies because the summation of the forces external is approximately equal to 0. Okay, so the initial momentum we have is just m times v, and then after the collision, the momentum we have is 2m times v final, so that v final is in fact equal to, notice the m's cancel out here, and you get v final is actually equal to 1/2 the initial velocity. Now they want us to calculate how much of the initial kinetic energy is lost. So the initial kinetic energy is 1/2 mv squared. The final kinetic energy is 1/2 times 2m times v final squared, and we just worked out what that v final was. Notice the 2m and the 1/2 cancel each other out there, so I'm going to go ahead and make use of that. And now I'm going to say that we have m times v over 2 squared, which equals 1/4 m v squared, like that. Okay. Now, if you'll notice, that is exactly equal to 1/2 of 1/2 mv squared. And of course, that's equal to 1/2 of k initial. So that alone tells us that we lost half of the initial kinetic energy. So that's actually a complete answer, believe it or not. Okay. Your book actually does it with, basically the numbers. So we can do that as well. What we're going to do is say, okay, well, we're still going to have 10,000 or 1.00 times 10 to the fifth kilograms times 8.0 meters per second. This is momentum. So I'm doing the same calculations I did up there, but now I'm doing it with numbers. That's going to be equal to 2 times 100 or 1.00 times 10 to the fifth kilograms times V final. You can see right now that the 100 times or 1.00 times 10 to the fifth cancels out, and we get that V final is going to be 4.00 meters per second. Now we can do the initial kinetic energies, 1/2 times 1.00 times 10 to the fifth kilograms times 8.00 meters per second squared. When I do this math, which you can pretty much do on your own, that's 32, that's 3.2 million basically. So we can do 0.5 times 1.00 times 10 to the fifth times 8 squared. That gives me 3.20 times 10 to the 1, 2, 3, 4, 5, 6 as suggested. Joules. So that's how many joules we have initially. Afterwards, we have 1/2 of 2 times 1.00 times 10 to the fifth kilograms. And actually, I should have put just a parenthesis there. I didn't need a square bracket, but I did need the square bracket in general. And then I'm going to take that and multiply it by v squared, which in this case turned out to be 4.00 meters per second. And that quantity is squared. So I can do 0.5 times 2 times 1.00 times 10 to the fifth times 4 squared gives me 1.60 times 10 to the 6 joules. So you can see that this is exactly equal to 1/2 of 3.20. Well, let me do that again. Times 10 to the 6 joules. So we get the same answer in both cases. Any questions on that? Now, in general, it could be a little bit worse than that. In fact, let me do this. I'm going to take this page and I'm going to copy it. And then I'm going to take this page and I'm going to paste it right here. So I paste the page right here. Whoop, I did it wrong. Let's go back. Yeah, I think I want to paste it here. Okay, there you go. So let me talk about two things in general in a one-dimensional collision. So if we had, for instance, M, a particle, let's say, moving with a velocity v, and then it collides and sticks together with a object of mass, let's call that m1 plus m2, and conservation of momentum dictates that the new velocity v final will be given by this, then what you find is v final is actually equal to m1 over m1 plus m2 times the initial velocity. So that's a typical final velocity from any perfectly inelastic collision. So for an inelastic collision, conservation of momentum basically gives us that. Now, kinetic energy. Kinetic energy initial is 1/2 m1v squared. And then final kinetic energy is 1/2 m1 plus m2 square times v final squared. Now I can plug in that v final squared. This is going to be 1/2 m1 plus m2 times, now I'm going to write in m1 over m1 plus m2. I'm going to square that, and I'm going to square the initial velocity. You can see what's going to happen is I have a 1/2 m1 plus m2 over m1 plus m2 quantity squared, and then times m1 squared, and then times v squared. And what you can see is this exponent of 2 will cancel out one of these, and what I will get is 1/2 m1 squared over m1 plus m2 times v squared. So now the change in kinetic energy divided by the initial kinetic energy is equal to K final minus K initial over K initial. So the K final we found was 1/2 m1 squared over m1 plus m2 v squared, and the initial was 1/2 m1 v squared, and then all of that, of course, will be divided by 1/2 m1 v squared. I'm going to get a common denominator for the two fractions on top. Notice they both have a factor of 1/2 and v squared. So I'm just going to pull that out in front. And not only that, I'm also going to pull the 1/2 m1 v squared from the bottom down there as well. So we can actually at this point go ahead and cancel out this 1/2 and this v squared just like that. And then all we have left in the bottom is the m1, and then we still have that numerator to deal with. So what's that numerator? Well, that numerator is m1 squared. Now I'm going to take this m1 that I have over here, and I'm going to multiply it by m1 plus m2 over m1 plus m2 like that, so that I'll have another denominator like I want. But now I've got to multiply this negative m1 and I've got to distribute it through those parentheses. So it's going to be minus m1 squared. Oops, I should probably stick to red. So it's going to be minus m1 squared for the m1 hitting the m1 term. And then the negative m1 is going to hit the m2 term. So it'll be negative m1 m2 like that. And then all that still has the denominator of m1 plus m2 right there. So we can see that the m1 squared is going to cancel out with the m1 squared. So this and this cancels out. And ultimately, what we can see is we're going to get basically negative m1 m2 over m1. Notice that's the m1 that was left from right here. And then that's going to be times the m1 plus m2 in the bottom. And that's basically it. Now, we can make a slight simplification by canceling out the m1 here with the m1 here. And finally, what we get is a general expression that the change in kinetic energy as a fraction of the initial kinetic energy is in fact just equal to negative m2 over m1 plus m2. So you can see that's a much more general expression for how much kinetic energy is lost when two things collide and stick together. Anybody have any questions about that? So that was just something I wanted to show you guys and see how you could work it out. In the simple case where we had M1 equals M2, you can see that the M2 and the M1 both being replaced with M would be M over 2M. So you literally get negative 1/2, which is exactly what we found earlier. Anyone have any questions on that? All right, let's move on to my next example. So billiard ball A moves with a speed, and this is very much like one of the problems in the book. So a billiard ball A moving with a speed of 3.00 meters per second in the positive x direction and strikes another ball of equal mass. However, this ball B is initially at rest. The two balls Whoops, I should probably stick with the same color. The two balls are observed to move off at 45.0 degree angles from, whoa, I should put that as from the x-axis with ball A being above the axis and ball B below. What are their speeds? What are their final speeds? So that's the question. So if I drew this on a diagram, which is obviously a useful thing to do, I would say this is ball A, and it has a velocity of 3.00 meters per second. Not only that, it happens to be moving parallel to the positive x-axis. And we're going to say that it's going to collide with particle B, which is at the origin and is initially at rest. But then what's going to happen is this. There's ball A moving with velocity VA prime. And this angle is 45.0 degrees. And then actually, I should probably make that a little bigger. Now that velocity is supposed to be parallel to that path there, but I did a horrible job with that. Let's see. So this is V B prime is that velocity, and this angle is negative 45.0 degrees. Okay. Now this is an actual 2D problem. And it's not necessarily elastic. It's pretty close. I want to point out to you guys that elastic collisions, though it has the word elastic in it, and that always made me think that two really, really squishy, bouncy balls would be more likely to be an elastic collision than two really rigid balls. But it turns out that's exactly the opposite. Pool balls are much more likely to have elastic collisions than spongy Nerf balls, for instance. Okay. So just keep that in mind from a physical standpoint. Now, what we have here is the summation of the forces external is equal to 0. Again, the friction is going to be fairly negligible. The air resistance and all that stuff's fairly negligible. But because of that, we're going to have conservation of momentum. So with conservation of momentum in 2 dimensions, I'll go ahead and show you how that is. But I want to tell you something. This diagram that I have drawn, it may seem like a special case. It's a special case in which one particle is sitting still and the other particle happens to be moving parallel to the x-axis. This is completely general from a physics standpoint because it's very trivial for us in the physics world to jump to a reference frame, for instance, in which the target particle, what we're calling B here, is not moving. So for instance, if we had the particle A moving to the right at 3 meters per second and the particle B was moving to the left at 10 meters per second, we could jump to a frame that was moving to the left at 10 meters per second. And in that frame, B would be sitting still, but A, instead of having 3 meters per second, would now have a velocity of 13 meters per second. And then we can also always set up the coordinate system such that we're moving initially in the x direction. So this is a completely general problem. Now, what I want to show you is what is conservation of momentum for the x direction. So conservation P sub x. What that's going to be is M sub A V sub A is equal to M sub A V sub A prime cosine theta A prime plus M sub B V sub B prime cosine theta B prime. I'm going to call that equation 1. Conservation of momentum P sub y is going to be 0 is equal to M sub A V sub A prime sine theta A prime plus M sub B V sub B prime sine theta B prime. And that's going to be equation 2. So that's our generic equations for conservation of linear momentum in 2 dimensions. So this is no longer a head-on collision, and it's not elastic yet because nothing was said about this being elastic. But what the method that we're going to use to solve this is actually quite nice. at least in the next problem. So right now we'll solve it in a very simple way, but in general, once I combine the kinetic energy, conservation of kinetic energy, because we're going to examine an elastic collision, there's a very specific way of solving it that will make life really, really easy. So what I'm going to do here is I'm going to take equation 1 and I'm going to write in what we know. Okay. So I can write with equation 1, I can write that, and they are identical. So I can go ahead and call the M's, M A equals MB is just plain equal to M. So I can divide both sides by M like this, and this MA and this MB is all going to disappear. And I can do the same thing here. And this M is going to disappear. So what I can have now is I'll have 3.00 meters per second is equal to VA prime cosine 45.0 degrees, and that's positive, by the way, plus VB prime times cosine negative 45.0 degrees, like that. Okay. And that's one equation. And then equation 2 would be 0 is equal to VA prime sine 45.0 degrees positive plus VB prime sine negative 45.0 degrees, like that. So you see, we really have two unknowns, VA prime and VB prime. And if we can figure out some way to simplify them, life would be easy. So what I'm going to do is take equation 2 and solve it for VA. No, I'll solve it. Yeah, I'll solve it for VA prime. So, whoa, Nelly. So if I solve for VA prime, I get VA prime is equal to VB prime times the sine of negative 45.0 degrees divided by the sine of positive 45.0 degrees. And of course, if you remember the way sine looks, let me refresh your memory. That's sine, like that. And you see that the sine of negative x is equal to the negative of sine x. So this is basically equal to negative VB prime. And I think that's about right. Let's see. Oh, no, I forgot a negative to begin with. This should have been a negative here, so that would have made this one a plus. So what we found out now is that the VA prime and the VB prime are in fact equal to each other. Now we just need to figure out what they are. So now I can take this result, which I'll call 3, and I'll say plug 3 into 1, and what we're going to get is 3.00 meters per second is equal to VA prime times cosine 45.0 degrees. And then the other one would have normally been VB prime, but since they're equal to each other, I'm just using VA prime for both of them. So now I get plus a cosine theta B. So that'd be plus cosine negative 45.0 degrees. But this is sine x. And if we look at cosine x, what you'll see is cosine's an actual even function. So it looks like this. So the mirror image is the same. So sine of 45 or cosine of 45 and cosine of negative 45 are both the same quantity. And that quantity is the square root of 2 over 2. So this part, whoa, Nelly. So this part is going to be the square root of 2 over 2. And this part is going to be the square root of 2 over 2. So we're end up going to get the square root of 2 times VA prime. So VA prime, which equals VB prime, is equal to 3.00 meters per second divided by the square root of 2, which equals 3.00 meters per second divided by 1.414. And that should be close enough. So if I do that, I'll say 3 divided by square root of 2. And that's super helpful because it didn't change it to a decimal. That gives me 2.12 meters per second. So 2.12 meters per second is equal to VA prime, and it's equal to VB prime. Anybody have any questions on that one? Okay, so that one was pretty easy because we only had two equations and we only had two unknowns, so it's really not that big a deal. It can get nastier though, so let me go ahead and work out in general what happens with a two-dimensional collision. So let's say two-dimensional collisions. And let's say if the net external force is approximately equal to 0, then P is conserved. So what we're going to have is exactly the same equations that I just put, but that one before was really nice because we had matching m's, so it made for another simplification. But the main thing is we're going to have m sub a v sub a is equal to m sub a v sub a prime cosine theta a prime plus m sub b v sub b prime cosine theta b prime, like that. That's going to be equation 1. And then equation 2, this is the this is the y component. So in this case, we're going to get 0 is equal to m sub a v sub a prime sine theta a prime plus m sub b v sub b prime sine theta b prime, like that. Okay, so that's just the case of it being an collision in which kinetic energy is conserved. If we add the elastic condition, things can get even nicer. But what I want to do right now is show you a surefire way that your book is trying to tell you, hey, this is the way that you can repeatedly use. So what I'm going to do is I'm going to take 1 and get all the A's on the same side. So I'm going to say get A's on one side of the equal symbol and B's on the other. You all right, Shawnee? Oh, it's coughing. I just had to check on it. So what I'll do is I'll subtract MA VA prime cosine theta from both sides in equation 1. So that's going to be MAVA minus MAVA prime cosine theta A prime is equal to MBVB prime cosine theta B prime. I'm going to call this equation 1 prime. I'm going to do the same thing with 2. This is going to be MAVA sine theta A prime prime is equal to, I'll put a negative in front of that, and that's equal to MBVB prime sine theta B prime, like that. Okay, now this is the part that doesn't necessarily seem all that helpful. Now watch what happens. Square both sides of each equation. So I'm going to square both sides. So 1 prime is going to become M sub A V sub A squared. So M sub A squared V sub A squared minus 2M sub A squared V sub A prime cosine theta A prime plus M sub A squared V sub A prime squared cosine squared theta A prime. That's equal to M sub B squared V sub B prime squared cosine squared theta B prime. Okay, I'm going to call that equation 1 double prime. So everybody follow what I did there? And I don't like how this B turned out. Okay, now that doesn't necessarily look like anything helpful, but in a second it will be. So now what I'm going to do is do the same thing for 2 prime, or for, yeah, with equation 2 prime, and this is going to give me equation 2 double prime. In this case, the negative is just going to become squared, and I'm going to get MA squared VA prime squared sine squared theta A prime is equal to MB squared VB prime squared sine squared theta B prime. Okay. Now, this again doesn't seem like that much, but if you look at specifically this term combining with this term and this term combining with this term, we can get some nice stuff working out. So for instance, I'm going to add 1 double prime to 2 double prime. When I do that, I get M sub A squared V sub A squared minus 2M sub A squared VA prime cosine theta A prime plus, now here's the part where we're adding the two, MA squared VA prime squared times, now parentheses, it's going to be cosine squared plus sine squared. I'm not even going to write what the argument of the sine and cosine are, because it's obvious that cosine squared plus sine squared is equal to 1. The same thing is going to happen on the other side. So I'm going to get M sub B squared V sub B prime squared cosine squared plus sine squared, like that. And of course, everybody knows that this quantity is 1 and this quantity is 1. Does that make sense to everyone? So now we can go ahead and write m sub a squared v sub a squared minus 2m sub a squared va prime cosine theta a prime plus m sub a squared v sub a prime squared equals m sub b squared v sub b prime squared, like that. So we've at least gotten rid of the square of the cosine, and this is going to be what I'll call equation 3. So that's a pretty big, important step. Now, if we want to allow it to be an elastic collision, then we can go a little step further. And let me show you what that is. So whoa, Nelly. If the collision is elastic, then we get 1/2 m sub a v sub a squared is equal to 1/2 m sub a v sub a prime squared plus 1/2 m sub b v sub b prime squared, like that. So we can actually add yet another equation, but this also allows us, for instance, if we happen to be lucky enough to have equal masses, then we can get rid of all the masses. But the bigger thing is that with this equation, you can actually solve, for instance, for VA prime and then plug that in, or the more smart one would be solve for VB prime and then replace that in equation 3 with the VB prime that we got in equation 4. And that gives you a nice ability to solve for one of the other terms, because now you're going to have VA prime and you're going to have a VA prime on the other side. And that's really your only unknown, that and cosine theta A. So let's go ahead and see if we can make use of this now that we understand this method. Notice the method that I used. I literally got all the MAs on one side and did that nasty squaring and then added the two equations, and that made us come to a space that was pretty nice. So that's what I want you guys to remember. This is what you're going to have to do when you're doing it. And now you have 3 equations, and therefore you're allowed up to 3 unknowns. So let's look at example 913. Example 913, this is a proton-proton collision. Now, there's a lot of times where microscopic or atomic particles are, really small particles like protons, neutrons, electrons, those sort of things. Generally speaking, they are often very much elastic collisions. The things that make them inelastic in general in collisions would be like, friction forces and stuff like that. Well, there's really no smaller particles. You're also not losing any energy because you got a dent in your proton. Whereas when you actually, get a dent in your car, that steals some of the energy and stuff like that. You don't have to worry about that at the microscopic level, but you still could have, for instance, a Coulomb potential or even a gravitational potential, which would be way smaller. But with this in mind, what we have is a proton traveling at 8.2 times 10 to the fifth meters per second. So a proton traveling at 8.2 times 10 to the fifth meters per second collides elastically with the stationary proton. Uh, one is observed. Whoa. To be scattered at 60.0 degrees. And they want to know what is the scattering angle for the other. And what will be their final speeds. Okay. So what we've managed to get is basically a problem not unlike what we had. In this case, I'm going to go ahead and start it over so you get to see yet another turn. So momentum in the x direction is going to be m sub a. Actually, they're all the same masses, so I'm just going to call it m. So m v sub a is equal to m v sub a prime cosine theta a prime plus m v sub b prime cosine theta b prime. I'm going to call that equation 1. P sub y 0 is equal to mva prime sine theta a prime plus mvb prime sine theta b prime, like that. And now I'm going to say, since it's elastic collision, I'm going to say kinetic energy as well. So, and this will be equation 2, by the way. So 1/2 mva squared is equal to 1/2 mva prime squared plus 1/2 mvb prime squared. That's going to be equation 3, but I can also get rid of all the masses. So now I'm going to say 1 prime is going to be equal to VA equals VA prime cosine theta A prime plus VB prime cosine theta B prime. And of course, I can go ahead and make that VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared cosine squared theta A prime. That's going to be equal to VB prime squared cosine squared theta B prime, like that. So that's another version of equation 1 prime. And then equation 2 prime, that's going to be negative VA prime sine theta A prime is equal to VB prime sine theta B prime. And of course, we can square that as well, in which case you'd have VA prime squared sine squared theta A prime equals VB prime squared sine squared theta B prime. So there's another version. And now we can also do the same thing without the actual 1/2s or the m's with regard to kinetic energy. So I'm going to call this equation 3 prime. And it's basically just going to be VA squared is equal to VA prime squared plus VB prime squared, like that. Okay. Now what I'm going to do is go ahead and add 1 prime and 2 prime. So So I'm adding just like I did before. So when I do this, I'm going to get VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared. Now here's the part where I'm combining it with the left-hand side of 2 prime. So this is going to give me the cosine squared of theta A prime plus the sine squared of theta A prime. And then on the right-hand side, I'm going to basically get VB prime squared. And in this case, it's also going to be cosine squared theta B prime plus sine squared theta B prime, like that. So this ultimately gives me VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to VB prime squared. Again, we just made use of the fact that sine squared plus cosine squared is equal to 1. So now we've combined those two. I can see I've got a VA prime, a theta A prime, and a VB prime all in there. And I'm going to call this equation 4. Okay. But now I can go ahead and make use of, I think I want to do this. Let's see. Yeah, now I'm going to go ahead and make use of equation 3 prime. So from 3 prime, we can see that VB prime is actually equal to, our VB prime squared technically, is actually equal to VA squared minus VA prime squared. So we can plug that in for VB prime squared. So I'm going to plug that into 4. And what I'm going to get now is VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to, now here's where I'm going to replace this with VA squared minus VA prime squared. So in doing that, I can now make a slightly different scenario. For instance, the VA prime and the VA, or the VA squared and the VA squared, are going to cancel out. So I can subtract VA squared from both sides. And then I'm left with basically negative 2 VA. I can say negative 2 VA VA prime cosine theta A prime is equal to negative 2 VA prime squared. In other words, I just took this VA prime squared and pulled it over here. It became negative, so that gave me 2 of those. And I should have an equals between them, so let me fix that real quick. So I have that. If I pull it to the other side, then I'll have an equals, and this would be negative 2 VA prime squared, like that. You can obviously see that one of the VA primes is going to cancel out, and so will the negative 2, like this. So ultimately, now all I have is VA cosine theta A prime is equal to VA prime. So using that as my angle, I can go ahead and say that VA prime is equal to VA, which we found was 8.2. Well, no, 8.2 times 10 to the 5th meters per second times cosine of 60 degrees. And with that, I get 8.2 times 10 to the 5th times cosine 60, close parentheses. That gives me 4.1 times 10 to the 5th meters per second is equal to VA prime. And then, of course, I can also use VB prime from that same equation where we solved VA squared equals VA prime squared plus VB prime squared. I can use that to figure out what VB prime squared is. So I can say actually, I'm going to keep it in blue. So VB prime is going to be equal to, from the VB prime squared is equal to VA squared minus A prime squared. That's equal to VA squared minus VA prime squared. So that's equal to the square root of 8.2 times 10 to the 5th meters per second squared minus 4.1 times 10 to the 5th meters per second quantity squared. And doing that, I'll say 8.2 times 10 to the 5th squared minus 4.1 times 10 to the 5th squared gives me 5.043 times 10 to the 11th. Whoa, nearly. Oh, that's really bad. Maybe that's right. Yeah, that's right. Now I got to take the square root of all that. Square root, answer. That gives me 7.10 times 10 to the 5th meters per second equals VB prime. And if you want to figure out what to do with the angle, we do know from, for instance, equation 2, sine theta B prime is equal to basically negative V sine theta B prime be negative VA prime over VB prime sine theta A prime, like that. When you do that, you can see that this quantity, the 4.1 over the 7.1 times the 0.866, gives me theta B prime is equal to negative 30.0 degrees. Okay, so that's how you solve example 913. Anybody have any questions on that one? Okay, pretty straightforward, right? Not too terrible. All right, so it's 6:34. We're supposed to go till 7:40. What I wanted to start next is just giving you a little rundown on what the center of mass is. So it turns out that the center of mass, if you think a little bit about distributing weights, for instance, on the seesaw, you'll notice that if you have two identical kids, then you can put one on one side of the fulcrum and one on the other side of the fulcrum. And if they're the same distance away from the fulcrum, then they'll balance. Now, if you had one kid that was twice as big as the other, you'd have to put the big kid closer to the fulcrum. And with a little bit of experiment, what you'd figure out is if the kid weighs twice as much, then the distance from the fulcrum that the big kid is should be half as much, and so on and so forth. So you get the idea that this mass times distance is something that's relevant. And because of that, we can go ahead and make a bold statement. Specifically, I can say the x center of mass is equal to m1 x1 plus m2 x2 plus dot 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 plus on up to mn xn. Now, that gives us, in some sense, mass times a distance. And we really want a distance to come out. So it's kind of reasonable to suspect that what we have to divide this by is the sum of the masses. So it's going to be divided by m1 plus m2 plus dot 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 plus mn. That's our x center of mass. And in fact, the generalization of it becomes the integral of x dm divided by the integral of dm. Similarly, the y center of mass is going to be m1 y1 plus m2 y2 plus dot 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 plus mn yn, again divided by m1 plus m2 plus dot 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 plus mn. Again, this generalizes to the integral of, in this case, it's going to be y dm over the integral of dm. Okay. Now, in addition to this, I need you all to understand something. dm can be equal to lambda times dl, or dm can equal sigma times dA, or dm can equal rho times dV, where this is the mass per unit volume. This is mass per area. And this is mass per length. Now, that can actually be a function. That could be a function of r, function of x, function of y, that sort of thing. But whenever we say they're uniformly distributed masses, then the lambda or the sigma or the rho becomes constants. But that's generally what we're going to use. And if it's uniformly distributed, all we have to do is just take a particular chunk of the matter that we're trying to find the center of mass of. And if we're talking about a rho, then we're going to take out a volume and we divide the mass of that volume by the volume, and that'll give us what we call rho. If it's uniformly distributed, it's going to be a constant no matter what chunk we choose. Same thing with the sigma. In that case, though, we're going to take a little area, a width and a height, and we're going to weigh it, and we're going to take that mass and divide it by that area in square meters. And since it's uniformly distributed, that has to be a constant. Or finally, if you just had a rod, you take the length of the rod and you take the mass of the rod, you divide the mass of the rod by the length of the rod, and that would give you lambda. And since it's uniformly distributed, that's always going to be a constant. So no matter what chunk of rod you took, it would always work out the same. So that's a little precursor. The main thing to know about the center of mass, though, is that it turns out from Newton's second law, if you actually did Newton's second law for a big object that has many, many parts, M1, which is located at X1, Y1, Z1, and M2, which is located at X1, Y, or X2, Y2, Z2, and so on and so forth, what you'd find is there's an exact equation parallel to Newton's second law, and that equation tells you how the center of mass of the system moves. So if the net external force acting on the system is zero, then the center of mass cannot move at all. If it was moving before at a constant velocity, it'll continue moving at that constant velocity. But if it wasn't moving before, it'll continue staying right where it was. So we're going to use that to find, actually, you'll be surprised, you can actually solve many problems that we solved with conservation of momentum. You can now solve them with just realizing that the center of mass isn't going to move. So I recommend you guys checking out the two problems where I said firing a cannon in a box. So if you look on your in your modules, you'll see two examples, one of which I solved using conservation of momentum, the other I solved using center of mass. Those are really the sort of a very high level of solving a problem. So do check those out at your earliest convenience. Make sure you've chatted me your first and last name. Everybody, of course, is free to go. Thanks for coming. And I'm going to wait here for the last person to leave. I did have some stuff that I wanted to explain to Giovanni as well as possibly Dylan. I'm not sure if Dylan's staying on, but anybody has any questions, stick around. You have a question, Jen, or are you good? Oh, she's out of here. Mark, did you have a question?
Yeah. Do you have a picture of class 201 on Thursday morning
Do I have a picture of what's that, Mark?
of the whiteboard of class 201
Oh,
on
yes.
Thursday morning?
Did you send me a text yet? Did you send me an actual text message, Mark?
Yes.
Okay. I think yeah, I can send that to you with that. Just send me another one and I'll send you. You're talking about what you missed on Thursday, right?
Yes.
Yeah, I'll go ahead and send that to you. If you just send me another one so I can remember which number's yours. Do you remember my cell phone number? I mean,
Yes,
don't
I
say it
have
out
it.
loud, but
Yes, I just sent you a text message.
okay. I got you. Okay. I'm going to send you a photo. And we didn't cover anything. We haven't had class this week yet, so we're free on that one. I do believe it would be.
And how far did you get in the textbook on Thursday? Like, did you went to like?
No, I didn't get very far. I think we finished. I want to say we finished that chapter, but that was about it. So let me look at this example. Yes. Yeah, we got through through example 20-4, 20-5, 20-6. So we're into chapter 20 and we got up to chapter 20-6.
Okay, so wait, are you talking about force between two parallel wires or?
Yeah, we did that. Well, we got prepared to do that, but we didn't actually do it with two parallel wires. All we did was showed how to calculate the forces. It was mainly about working with people with the right hand rule. So that's probably something that's not really easily done except in person. But we'll be able to meet tomorrow. That'll be a good time for you to catch up on that if you're a little bit behind.
Okay. Yeah, I'm gonna read up on those 3 chapters today.
Okay, no problem. Have a good one, Mark.
Thank you, Professor.
Thank you, sir. Have a good one. Giovanni. And actually, Dylan, did you have a question too? Giovanni has something I need to talk to him without the recording showing specifically because it's about some test questions.
Oh, okay.
And I just didn't want it recorded. So I can stop recording and that's fine. But if you had something that needed recording, I wanted to make sure I got it from you first. So did you have any specific question, Dylan?
I was just gonna see if you could, I don't know, maybe better explain what these concept questions are trying to.
Yeah, gotcha. That's what it was. Yeah, I remembered you telling me now. Yeah, I can definitely do that on in real time. And if Giovanni, if you're in a hurry and you got a split or whatever, I think it would be better if I did this part first, and it'd probably help you as well. If you end up having to leave though, you can just send me a text message, and I'll try to set up a private Zoom session with you as well. But if you can wait around for a couple minutes, we can do that. Dylan, you want to go ahead and share your screen?
Yeah, just give me 1 second.
Okay, I just made it where multiple people can share.
Here. Okay, so this is
Gotcha.
I guess the setup.
Okay, two toy cars shown in figure with masses as given in the figure. One's 1,000, the other one's 800, are ready to race. Both cars begin from rest. For each question, state whether the correct answer is car A, car B, or whether the two cars have equal values. So for the next three parts, assume that the car's motors supply the same force to each car over the course of a 1 meter race. Okay. So which car crosses the finish line 1 meter away first?
Okay, so I got that one because obviously B's lighter, so it's gonna go faster.
Exactly.
Okay, so I got that one. But then when it got to which one has the larger kinetic energy, which was the mv squared.
1/2 mv squared, right?
So I assume since the lighter one is going to have a higher velocity, it would have a higher kinetic energy.
Ah. So what happened here was, remember the part where they said assume the engines had the same ability to basically do stuff or whatever.
Yeah.
Because of that, well, actually, scroll up a second so I can read that wording again. Two cars shown. For each question, state whether. Okay, for the next three parts, assume the car's motors supply the same force to each car over the course. Okay, so the same force means basically that the lighter car is going to get the bigger acceleration. So the lighter car could actually end up having a higher speed, but the total amount of work done, since the cars are the same having sort of the same engine capacity, there's going to be a certain amount of work done from the start to the finish, and that amount of work is going to turn out to be, according to the dang it, uh the work energy theorem, the total work is just going to be equal to change in kinetic energy. So that means the change in kinetic energy is going to have to be the same. That's why they have both cars have the same kinetic energy.
Okay, so how would you like set that up to, you would just do the 1/2 mv squared for the second car minus the first car?
Yeah, what you're calculating is the net work done on car A. And according to the work energy theorem, the net work done on car A is equal to the change in kinetic energy of the car. And the same thing with the net work done on car B is going to be the change in kinetic energy. But because of that change in kinetic energy and the fact that these engines have the same capacity, that means the work's going to be the same for both of them. So the left-hand side of work equals change in kinetic energy are equal in both cases. So that means the right-hand side in both cases has to be equal.
Okay, see, I was thinking since the mass isn't squared and velocity is, the one with more velocity would have more kinetic energy.
It is, but the very reason that it has more kinetic energy is because the very reason that it has more velocity is because the mass is so much smaller. And at the end
So
of the
they
day,
balance.
Yeah, but what actually has to happen is the work goes into changing kinetic energy, and the net thing is that the kinetic energies are going to be the same. One of which is done by having a large mass at a small velocity, and the other one's done by having a small mass at a large velocity.
So if the same work is done to two objects, no matter the mass, no matter the velocity, it's the same work done to both. They will both get the same kinetic energy, but the result may vary.
Yeah, the speeds are going to be very different, and therefore one could be faster than the other, but the kinetic energies are the same.
Okay.
Yeah.
And then the next one is which one has the larger momentum? And then again, I assumed something heavier has a larger momentum,
And
which
in that case,
it is
yeah,
true.
man, that's a really a hard one to help you see it though. So, which car has a larger momentum when it crosses the finish line? And car A was the 1,000 kilogram one, right?
Yeah.
Yeah. Okay. So in that case, what we have is
Because it tells you to use the force and the time interval over which the force is applied. And then basically you're using the force
the
to,
impulse thing, right?
yeah. And I wasn't, that's where I see it goes between these three different things. And I wasn't sure how they kind of relate and how to go in between the three.
Yeah, so in this case, if you look at what impulse is change in momentum. So that's the simple case where it's P final minus P initial. But the other side of the equation is basically an integral of the force over a time period delta T.
Yeah.
Since the engines are identical, you would expect that the force they can supply are about the same, and the time over which it could apply is about the same. So you'd expect that the momentum in the heavier car, well, no, that gets you back to where it was. Let's see. Let me look at this hint. It says since both cars start from rest, the impulse applied to each car is equal to its final momentum. Recall the impulse is given as the product of the applied force and the time interval over which the force is applied. You are given the equality of the forces in the description of the race. So the time is the subject of part A. I don't know what the
Yeah. They want you to assume that because the lighter car finished sooner, it was going
Oh
for a
yeah,
shorter time, so it didn't build up as much momentum.
that's right. Because they asked when it crossed the finish line, not at the end of an equal time interval.
And that's what this next part's about, which I was also gonna. It asks you about time, and
Yeah,
going
that
between these three
that
is
one's kind of
confusing.
neat. Okay, what's the next one then?
So it's the exact same question, except instead of a finish line, you have a 10-second race.
Ah, gotcha. So now in the 10-second race,
B is still faster, but they travel for the same time. It's just saying B is going to be faster after 10 seconds because it's lighter.
exactly. Yeah, that works.
Then
Part E, after 10 seconds, which car has the larger kinetic energy? In that case, the A or the B car, the lighter one, has the bigger kinetic energy, which is what you got. So that makes
well, I
sense.
got that because I got it wrong. So,
Okay.
but that's what I don't get is if you have the same work, why does it matter if it's done over a short time? If it's the same work,
It's the same work but remember, work equates to kinetic energy, not to change in momentum. Change in momentum is related to impulse, which is the force times time, whereas the work is like the force times distance.
yeah, but when we said earlier that if they both get applied the same amount of work, uh, their kinetic energies are going to be the same.
Exactly. But this one isn't the same amount of work because car A is going faster. So 10 seconds means it can go a larger distance, and the work is therefore potentially larger for the faster one because it's force times distance, not force times time.
Huh.
Do you see the difference there? You're right. You're thinking of everything you're supposed to, but the deal is when you're doing a 10-second interval, it's very likely that the 10-second intervals with the equal engines is going to make them have the same momentum at the end, but not the same kinetic energy.
I guess that's where I'm losing something along the way.
Yeah, so think about again, work is what equates to the change in kinetic energy according to work energy theorem. So you got the integral of f dx is equal to change in k. The f is going to be the same. The dx on this case is different though, because the dx on the B car, which is lighter, can ultimately result in an integral over in 10 seconds is going to be over a larger distance.
Okay, and yeah, and since work is force over a distance, the longer distance means you need more work to get there. But since before we were going a set distance, it didn't matter how long it took to get there, it was still going to get there, so it took the same amount of work.
Exactly.
I got you.
Yeah, that's not an easy one to come up with on your own. I totally get your difficulty here. After 10 seconds, which car has the larger momentum? So yeah, in this case,
And since
again,
it's
it's
work over,
force
it's
times
force over
delta
time.
t. Yeah.
They both
So
have the same force, they both have the same time. Obviously, they both have the same momentum, right?
yep.
Okay. And then yeah, see, and then the next question is basically the same, but it's a variation of the same where it's two hockey pucks.
Right.
One weighs what is it? One
Uh,
3 times as much as the other.
I'm glad they wrote out Brunhilde. I always wondered how you'd spell Brunhilde.
That's an actual person's name. Okay.
Yeah, I'd heard it before, but I'd never seen it spelled. So, yeah, I was looking to see the players exert equal constant forces of magnitude F on their pucks directed horizontally to the finish line. They start pushing at the same time. Each player has his or her buck until it crosses the finish line a distance D away. But they did have different masses.
Yeah, it says puck A has a or puck B has a mass 3 times as great as puck A.
Okay, so it's playing the opposite role of B before.
Yeah. Then it's which one will reach faster or first. A again, it's lighter. Um,
You let A, let K be the magnitude of the kinetic energy of puck A at the instant it reaches the finish line. Similarly, KB is the magnitude of kinetic energy of puck B at possibly different instant and it reaches the finish line.
and it's the same, I guess, as before, since it's going over a distance and not time, it's going to be the same.
Right. So you get the kinetic energies equal. Okay, that makes sense.
Yeah.
That's real. Yeah, that's tough.
I'm
I'm
trying to
glad you
find
got me to look at this because I haven't looked at these in probably a couple
there,
semesters.
there was one with a hint that was kind of weird that I didn't get.
Compute the ratio of the pucks.
Oh yeah, like this was weird. It's asking you to do the ratios of their momentum and the velocity and stuff, like they're the mass and all that. And the hint
Gotcha.
confused more than the question did.
The momentum of an object is the product of its mass and velocity. From the problem introduction, you know, ma over mb is equal to 1/3. Find fa. Uh, the reason they both started at rest. So part of the reason you're doing this is F equals ma is another way you could look at it. But they're really wanting you to stick with the F equals delta P over delta T. So
Yeah, but I'm wondering because it asks you to find the ratio of the velocity A over velocity B, and they get a whole number. Or not a
yeah,
whole number, but they get an actual number, but we weren't given any starting numbers, so I have no idea where that came from.
because the kinetic energy goes like V squared, that's 1 over the square root of 3. Or it is the square root of 3. If I remember correctly, let's see.
Oh,
Yep, that's what it is.
yeah, I was real confused with how they did that, so I didn't understand.
Yeah, it helps if you're a little familiar with random square roots and stuff.
Yeah,
I'm a nerd, so I pride myself on knowing that kind of stuff. But
yeah, this book, at least in his last couple chapters, wants you to take ratios of things and like of formulas, and it's really weird.
yeah,
It's confusing, it makes it
it's a
difficult.
nice thing. That's the way we ask you to do it when we do things like, what if I double the radius or double the distance away between two gravitational attractive objects? You can put them in as M1, M2, R1, and R2, and that sort of stuff, and then divide one by the other, and that tells you definitively exactly what factor. So it's good that they're getting you to do that, but if this is the first time you've seen it, then heck yeah, it's confusing as crap.
Yeah, especially just trying to take the ratio of a formula and then apply the ratio of a previous formula to a like how they did the previous ratio of mass to now they want you to apply that to the ratio of the velocities. I wasn't even sure how to deal with that.
Right. Yeah, so with this one, it ends up becoming the product or the ratio of the masses is inversely proportional to the ratio of the velocities squared. And that's how you ended up getting 1.73 as opposed to, 3. It would have been 3 if it wouldn't have been velocity squared, but it is the velocity squared, so you had to do the square root. Uh, yeah, I need to spend a little bit more time looking at these because I know this, I didn't cover this well enough for you to just get this on your own.
Oh, that's how all the conceptuals are. They are,
They're really brutal.
oh yeah. I've had to do all of them multiple times to even get a decent grade on them because they go way beyond anything the book or any examples
Yeah, I
do.
haven't looked at these, like I said, in at least a couple. Actually, I haven't looked at them at all since we switched to the fifth edition. So they
Yeah.
might even be quite a bit different from the fifth edition. But I think I think I chose to keep doing the fourth edition on this. But yeah, don't feel so obligated to get that great score. I mean, it sounds to me like you're a problem solver, so you kind of are not completely at liberty to just quit at any time. You're kind of stuck, obsessed and compulsed to do it anyways. But if they get hard like that, if you're spending a whole lot of time on just one problem, let's say if you're spending more than an hour on a single conceptual group of problems, then that's probably a time where you need to contact me or just, go broke and say, that's enough. I'm just going to take this grade. Because that's what I was trying to tell everybody is I don't want you focusing so hard on making sure you get 100 because occasionally they even have errors in this. I haven't found, to be honest with you, I don't think I found but maybe one error in the conceptual problems. But again, that was years ago. So I'm not sure how good that is, but that's part of the problem is when you're trying to get a perfect score, sometimes they're literally forcing you to do something incorrectly so that you can get that perfect score. So just shoot for a 70, 75 and call it quits at that point.
Okay. Yeah, because it says it should take like maybe an hour to do the conceptual, and it always takes me way longer because the way they ask stuff and the way they want you to, it's usually all formula stuff. There is no units,
Yeah,
no numbers or anything, and it's just
I
they
would
want.
say you're definitely way better off for having done what you've done, but at the same time, I would say from here out, I wouldn't spend as much time doing it. But the fact that you're looking over them and you're learning how the wording is so different, and I think that's what you're pinpointing here. That's a key thing that a lot of people don't get from taking their science class. So it's good that you are doing that.
But yeah, that's pretty much all I,
Okay.
I had a question on this. I hadn't gotten any further into it yet, so.
Yeah, so keep track. Remember, the integral of f dt is quite a bit different than the integral of f dl or dx, and that's sort of what these were hinging on. But that being said, it's still it probably would have taken me a couple times to get through that.
Yeah, and they also wanted you to one of them like this one says the simplest way to do it, would you use F equals ma, would you use one of the kinematics, or would you use the work energy theorem or conservation? It's like how I don't even know how you would know which one's the easiest to use because obviously
Yeah,
the ones I'm more familiar with would be easier.
yeah, and that's I mean, they're really wanting you to use the work energy theorem for obvious reasons, but at the same time, most people when they just finish chapters 1 through 4, 1 through 5, they're really pretty good at F equals ma and kinematics. So
Yeah.
they definitely want to use A or B instead of C there.
All right, well,
Did you want to stick around for what I was going to do with Giovanni? Because this is actually something that's kind of a big deal.
yeah, I can.
Okay. Let me go ahead and I'm going to steal the screen from you for a second.
Yeah, let me stop. There you go.
Thank you, sir. Giovanni, you still there, bud?
Yeah, I'm still here.
Okay. So what I was going to tell you, and here's going to, once this comes back up, I'll go ahead and stop the recording process. So I did pause. Uh-oh. Are y'all not seeing my screen now? Because I think I just paused my screen share instead of.
I see the blank page.
Okay. You are seeing that then. That's cool. I was trying to pause the video. Let's see. That didn't help. That didn't help either. Mm. Breakout room, nothing there. Okay, I'm probably just going to have to deal with this in post production, so I'll cut the video out then. But what you were asking about earlier, Giovanni, there's a thing where you have x of t is equal to, let's say, 3t minus 1t squared, and they're asking you for the average speed. Between t equals 0 seconds and I want to say it's t equals 2.5 seconds, something like that, maybe. But here's the kicker. With this x of t, you might not realize it, but this is sort of like y equals 3x minus x squared. And if you find a minima or a maxima, you could do that by saying dy over dx is equal to 0. That's going to give you 3x minus 2x is equal to 0, or excuse me, 3 minus 2x is equal to 0, because the derivative of 3x is just 3. So you get x is equal to 3 halves. Now, what that means is it's either a maxima or a minima. And of course, you could say d2y over dx squared. The derivative of 3 minus 2x would be negative 2. So that tells you that since it's negative, it's a minima, if I remember correctly. Y equals x squared would be a minima, and that's positive. So that's a positive gives me a minima, so a negative must give me a maxima, something along those lines. But what that means is if you were to graph this graph as x and t, what you're going to find is right about, let's say this is 1, this is 2, and this is 3. Somewhere about 1.5, you're going to find that the function is like that. So what's going to happen is it's clearly a parabola. So maybe the function looks like this, right? Now, because they asked for the average speed, what you have to do is figure out what the total distance was. So because average speed is equal to distance traveled divided by time taken. So the distance traveled, clearly this one went up. Let's just assume this is 1 meter, say. It's not really, I'm just doing it. So clearly I went 1 meter up and then I went 1 meter back. So the average speed would be 2.0 meters over the total time. If the time was 3 seconds, like I've drawn here, then that would be 3.0 seconds. So this would be 0.667 meters per second would be the average speed. The average velocity, on the other hand, would be x of 3.00 seconds minus x of 0.00 seconds divided by 3.00 seconds. But you can see here that x of 3 is equal to 0 and x of 0 is equal to 0. So you just get 0 meters per second. That's the key thing that many of my students are missing, if not all of them. Whenever you have x of t, if it's linear, then there's no problem because you know it's just going to do this or something like that. But once it gets quadratic, it could do this or it could do this. But once it gets cubed, it could even do like this. And if it gets to the fourth power, it could even do like that. But you've got to look for those maxima and minima because the distance traveled is if the person reached a max x of 5, then they've already walked at least 5 meters there. But if they had done something like this curve right here, then they might have went 5 meters and then back 2, so that's 7 meters, and then ahead 3, so that's 10 meters, and then back 1, so that's 11 meters, and then ahead by 3 meters, so now that's 14 meters, and then all the way back here, maybe that's 4 meters, so now we're up to 18 meters. Whereas if you were actually doing average velocity, it would just be this distance right here. Whereas average speed would be like 18 meters over the time, and the average velocity would be, this itty bitty thing, which is maybe 3 meters. So that'd be like 3 meters over the time. Does that make any sense to you guys?
Yeah.
So that's the key thing that I wanted to point out to Giovanni and other students too. So hopefully that'll help you a little bit. But yeah, whenever you do x of t and you're trying to find the average speed, remember the average speed is innately different than the average velocity. For instance, if you hit a home run and you sort of blindly start your timer when you accidentally step on home plate as you run to first, and then you come back and run to second, run to third, and then come back to home, the net distance you traveled is 4 times the length of the bases. And the average speed would be that 4 times the length of the bases divided by time taken. The net or the average velocity, on the other hand, would literally be 0 because the distance is just the change in position. And the change in position from home plate to home plate is 0. Does that make sense?
Yeah, I know there was one question on the test where it asks you about the speed and it gives you a negative and positive answer.
Yeah, that's the same one that Giovanni was talking about.
Well, and then if you pick the negative answer, it's wrong because speed is scalar. But
Right.
if they wanted to do that on the test, then throughout the entire Pearson stuff, they shouldn't refer to everything as the speed because that gets you,
Yeah.
it makes you stop thinking about that. And then all of a sudden on the test, oh, now they care to use it properly. It's
Yeah,
like
and I've got to look back at that because now you and Giovanni both said that. So I'm wondering
that's
if
the only
maybe there was
reason
a
I got it
different
wrong.
problem that I hadn't considered. But the one I worked did have a positive and a negative same answer, but the answer I got was like entirely different from one of those.
Oh no, the answer on the test is either negative 0.5 or positive 0.5. I put
Okay, gotcha.
negative because that's the first one I saw,
Yeah.
but that was wrong. It should have been positive because speed can't be negative. But
Gotcha.
throughout like any of the stuff online, they say speed 100% of the time. And then now on the test, it's like, well, we're gonna go back to actually caring that speed's different,
Yeah.
and we're gonna. It's basically there to say, hey, we know you forgot this. We want you to get this wrong.
Yeah, exactly. Well, actually, in light of you saying that, I'm gonna go back and look at it. I was actually planning on giving you guys some points for a couple of those problems, anyways. I just haven't done it yet because not everybody's taken it. Giovanni, I will be addressing that too. If it seems like there's a different problem, and it sounds like it is, then I'll definitely be looking into not only giving you points for that, but giving you points for other ones that I'd already talked about. And I also mentioned to him, Dylan, that I'm planning on trying to figure out some way to give y'all either an additional assignment or something to improve your face-to-face test scores. I'm still going to drop the one lowest, and we're probably going to at least have one more before Thanksgiving break. So hopefully that'll remedy a lot of this
If
stuff.
you want, I mean, the problem you did is the problem. I'm looking at it right now.
Oh, you are?
And it's, yeah, the answer is the position of a function or position of an object is given as a function of -3 t plus 1 t squared. What is
Yeah.
the average speed? T equals 0 and t equals 2.5. And your answer choices are -0.5, 0.5, and then 2, 2.6, and 1. So yeah, the answer I got was 0.5.
And did it grade it wrong?
Well, I put -0.5 because that's the first one I saw.
Gotcha.
So I assumed they wanted positive 0.5 because speed is.
Right. I'm trying to remember if no, that wasn't it. Let's see if it was this class. Nope, that was this class. Let's see if this one. Nope, that's the stuff I did with you. Yeah, I was trying to look at, I seem to recall the answer that I got for that one was 2.66, but I was trying to see if I could find it. And, but I don't think I kept it because I knew there was a problem with the test and I couldn't record that one specifically because people still hadn't taken the test. But does that answer your question there, Giovanni?
Yeah, it does.
Okay. Anybody else have anything? It seems like my supper might be ready, so I might get ready to split.
I
But
was
I
just
want to
gonna
make
say,
sure
'cause
y'all don't have any other
what
questions
I
for
did
us.
with that one was I just solved it for the position in each time.
Mm-hmm.
And then that's how I got to the 0.5. I don't remember I have the calculations I did somewhere in here, but
Yeah. Actually, I
because
can.
the way you did it was looked different than the way I did it.
Yeah. I'm going to pull up that right now since you and him both, I can pull up either one of your tests and see that specific question. So I'm going to do that real quick and just see exactly which one and what the answer was. There you go. And I'm going to do speed grader. This is test 4. Ah, yes, it was. Okay, so the position of an object is given. Actually, I can share this. Let's say stop share. Now I'm going to say share screens. So this is the one I was talking about. And it actually is really easy for you to see, but notice the answer is actually 1.30, not 0.5 or -0.5.
Huh.
And if you did this, let's do Desmos. Now, I'm not saying you can use Desmos during a test, but you are allowed to use a graphing calculator, so that's certainly fine. But what we're trying to do is say negative, let's say y equals -3x plus x squared. And you see, basically, in this problem that we just did, which was, excuse me, no, not that one, there it is. They wanted it between t equals 0 and t equals 2.5.
Mhm.
So 2.5 would be roughly here. So the distance traveled there, notice you went a distance of 2.25. And then you went back to 1.25. So that's another meter. So basically, what that's supposed to be is 2.25 plus 1 gives me 3.25. And then 3.25 divided by 2.5. 3.25 divided by 2.5 gives me the 1.3 that you were talking about. So it's this minima thing that really was the problem. It wasn't the minus and the positive. Yeah, that would have been kind of jerky if they did that and then all of a
I
sudden they
thought
ignored you.
I thought since it's giving you the function as a position of t, you could just put in the t for like t equals 0, you'd put in for t, and that'd give you that position at.
Yeah, it does give you the position, and the position is technically called what we call the displacement. But to calculate an average velocity, you do displacement at the end minus displacement at the beginning, and then divide that by the time taken. and that should give you a vector quantity. But when you do speed, you just need the total distance traveled, and that's 3.25 in this case.
Huh, yeah, because I got 0 as the first distance because there's 2 t's and the first variable 0. So
But wouldn't you have to divide it by time?
Yeah, so if you looked at this graph, the distance down to here was 2.25, so that's one distance it traveled. And then when they got to 2.5, it went to negative 1.25. That's 1 meter away from the negative 2.25. So the total distance traveled was 3.25. Now you take that 3.25 and divide it by 2.5, and that's where you get the 1.3. Does that make sense, Giovanni?
yeah, I'm still
Not real. So
yeah,
when
I'm
I
still not
did,
understanding that either.
so
Okay.
because the way I did it, right? Because if it gives you the position, I mean, you would just have to plug in 2.5 seconds, and that would give you or I guess the position, not really the distance, right?
Right, that gives you the position. And you need to figure
Okay.
out for speed, you need to figure out the distance traveled, not the change in position.
Okay, I get it. I get it.
Yeah, the change in position is what you're doing when you're doing average velocity. The distance traveled is what you're doing when you're doing average speed.
Yeah, it just gives you where it is, not the distance traveled.
Exactly. And it's weird because sometimes you have to revert to, like I said, graphing it. What I normally do is I look at it as a square and then I find the minima. And if the minima is between the time intervals or within the time interval that I'm thinking of, then I actually try and take and graph a couple points out and then estimate how far I went vertically. Because the x-axis is really the only motion it's going. Everything's going parallel in some sense to the x-axis. So you just do that. 2.25 is one distance, and then 1.00 is another. So hopefully that helps you.
Huh.
Yeah, it does. I just assumed that since the when T zero, it was zero, and so I just assumed it was just sort of like one whole motion instead of going back and forth.
Right. Yeah, that's very, I mean, that's literally what probably 90% and maybe even 95% of all my students have ever done. They're always making that careless mistake. That's why I tend to put these on there specifically to sort out, do they understand that average velocity is displacement divided by time, whereas average speed is distance traveled divided by time.
Yeah, I just assumed that since the first one was 0 and the second was 2.5, that's the position. So to get to that position, it traveled,
That
that
distance, right?
2.5. It traveled this distance since it's giving me the function
Yeah, the x of t. Yeah.
because that's
But
how
yeah,
I
that's how
remember.
you have to do that. As long as you know now, that's what really matters.
Yeah. Okay. I
All
guess.
right. Well, y'all have a good one, guys. Thanks again for that. And I will hear from you again Tuesday. Keep an eye out for your emails because I'm probably going to have some stuff for you guys to do to try to improve your face-to-face test scores.
Okay.
All right. Thanks again.
Yep. Thank you.
Have a
Later.
good night.
Good night.